Hello everyone, we are Team Selene and we are presenting the Martian Aquaponics module prototype. My name is Edgar Reyes, I'm the communications officer. With me today is Aaron Sifidif, the team lead, Christian Puckett, the treasurer, and Christopher Nobiger, the R&D lead. Now what you see is a quick overview of our presentation today. Many of you may be wondering what our actual topic is for TSGC. We are presenting the initial Mars base. Essentially, we are tasked with designing a base and then looking at a specific module within that base and performing detailed design analysis on it. Now, many of you may be confused and wondering why Mars? Well, NASA has been wondering about Mars and colonizing it for the future for quite some time now. The reason being because of its proximity to Earth as well as the fact that it has water. Now, as we all know, humans need food, water, air, and shelter to survive. For this system, we will be looking at the food and the shelter. As you can see here on the right image, you can see the fact that we'll be using radiation covering. It will be modular, and the fact that we'll be using geodesic domes in order to distribute the pressure and stresses of the system. You can also locate the fact that the aquaponics module will be within a specific part of the base. I will now be passing off to Aaron to talk more about the aquaponics module.
You may be wondering, what is an aquaponics module or cycle? So aquaponics cycle is basically a garden on top of a fish tank where the fish create waste that is turned into fertilizer for the plants. And in turn, the plants actually filter the water. So the fish provide nutrients for the plants and the plants clean the water, and it's a continuous cycle. Through our research, we were looking up as far as Mars specifications and for a healthy habitat for tilapia and fish. We found that 3 gallons of water per 1 pound of tilapia was feasible for a good living environment and a 1-to-1 ratio for plant to tilapia. This chart here shows some of the water requirements that we found for a healthy living environment for the plants and the fish, as far as the dissolved oxygen, temperature, pH, and ammonia goes. So with this information and with the theoretical equations and calculations that we found, we implemented that into a UI, or a user interface, utilizing a MATLAB program. Within this MATLAB program, the user can put in specifications for their aerator, lighting, or the heater, and the output of the user interface will let the user know whether the parameters of their system is feasible for a healthy living environment for the plants or the fish.
So in order to collect the data from our physical system, that we built and programmed a temperature controlled relay with Arduino that displays one of 3 warnings based on temperature input. If it's too cold, the heater's on. If it's above the threshold, the heater is off. And if it's within the acceptable range, the temperature is nominal. This info is displayed in the serial monitor, as seen in image number 2, where the output of the serial monitor is read by a third program called PuTTY, that then converts this information into a text file, which then can be opened in Microsoft Excel to plot the temperature change over time. Now, this is just the digital control of our prototype. Our actual prototype is based on accessible existing materials. We have grow lights for the grow bed, an aerator in the fish tank, heaters in both the sump and fish tank, and pumps in both the sump and fish tank as well.
In our fish tank, we have 2 tilapia that are 1.5 pounds each. Both in our sump tank and our fish tank, we have 2 200-watt heaters that are controlled by the Arduino, as mentioned by Mr. Christopher, and then 2 water pumps in each one, pumping 120 gallons per hour. This may seem high, but this is due to our head height that is needed to push the water up. Just in the fish tank, we have an aerator that gives the fish dissolved oxygen. And then also in the fish tank, we have a float switch that utilizes a 12-volt relay, 3 power outlet, and a float switch. This helps prevent overflow inside the fish tank. And then for the grow bed, we use 2 full spectrum grow lights that give the plants all the colors that are needed. Also inside of this grow bed, we use hydroton, which are fire kilned clay pellets that act as a soil to keep the plants from washing away. This also acts as a pH neutralizer for the water. For the sump tank, we use the sump tank as a 2 fail-safe system in conjunction with our float switch. This allows any water that may overflow to empty out inside of this sump tank, and it also acts as a filter, keeping sedimentation inside of this tank and allows it to settle.
Now, to conclude our work, this novel idea will allow for fresh food production for the astronauts, therefore increasing their quality of life. This system is theoretically feasible as long as the proper equipment will be implemented on Mars. Now, please direct your attention to this video about a quick prototype.